Alright, today we're going to have a look at extension 2 inequality proofs. Now, this is where we're going to start to get to the ridiculously hard questions in extension 2, which is why we're going to spend a lot of time on inequalities, and we're going to look at many different scenarios. So inequalities is a great source of hard yet simple proofs, and it will separate the top students from the very top students. Now, in the old syllabus, this formed the basis of the hardest marks on average of any topic, and yet the final solution was pretty short and simple. Now, don't quote me on this, but I'm pretty sure that these questions in the old syllabus were from a topic called Harder Applications of Extension 1. It wasn't a topic on its own. I remember when I did this in school, we didn't really learn these. We just had to work through it ourselves at Harder Applications of Extension 1. So be pretty grateful that this is now a topic on its own, where you're actually going to learn processes of how to do this, so at least in my opinion. So a wise man once said that a proof is an argument that convinces one of your peers that a statement is always true. A better proof also convinces a suspicious peer that it is true, and helps a less able peer to understand why it is true. Now, these questions are quite hard to come across, so I'm just going to say now that all of these questions come from a person known as Steve Howard. He makes an amazing textbook, and I might write that in the description just so I don't get in trouble. But all of these questions come from his textbook, and it's an amazing textbook that I would recommend everyone has a look at. Okay, so let's have a look at how we prove these types of questions. So we're first of all going to start with an inequality or an equation that is known to be true. Now, this is what we call an axiom. An axiom in mathematics, I think I wrote it down here, is a basic assumption that we accept to be true. One of the best assumptions that we're always going to use in inequality proofs is the axiom that r squared, anything squared, is greater than 0. Now, if you're stuck with any of these questions, often it's good to work from the conclusion back to the original question and then write it out in the correct order on your statement. Okay, why do we swap? Sometimes we swap the inequality. When we divide by a minus number, we swap the inequality. So when we perform an operation on an expression, we might change the order of the inequality sign, or we might not. So in summary, we're going to leave the sign alone if we perform an operation that matches a monotonic increasing function, so it's increasing only, such as addition, subtraction, multiplication by a positive number, or division by a positive number. So for example, we could say that x is greater than 4, which is greater than 2, because 4 is greater than 2. So we have x is greater than 4, then we could say greater than 2. And the next line, and it is still true because 4 is greater than 2. We want to swap the sign if we perform an operation that matches a monotonically decreasing function. That means the function is only ever decreasing, only ever has a negative gradient, such as multiplying by a negative number or dividing by a negative number. Or we might need to get more information if we wish to perform a operation that matches a function that is not monotonically increasing or decreasing, or is continuous, such as taking the reciprocal or a trigonometric ratio. Alright, so we're going to have a look at what happens when I perform these basic operations. So multiplying by 3, our inequality stays the same. That's because multiplying by positive is an increasing function, it stays the same. Dividing by minus 2, we swap the inequality. That's because minus 2 is a decreasing function. Take the tangent, so we're differentiating and finding the tangent at a point. We don't really know because the tangent is a discontinuous function, so we need more information here. Taking the negative reciprocal, we need more information. And that's because the reciprocal of a function, and we've got x, its reciprocal is 1 over x, and 1 over x is a hyperbola, which is a discontinuous function at the x and y axis. And we've set up here that we need more information if we're doing a discontinuous function. Taking the square root, it stays the same, because if you take the square root, first of all, you can only take the square root of positive numbers, and if you take the square root of a number, it's still positive. Of course, we're only talking about real numbers here. Okay, question number 1, we've got if a is greater than b and it's greater than 0, so that's telling us that both a and b are greater than 0, but a is greater than a is greater than b. Prove that 2 to the power of minus a squared is less than 2 to the power of minus b squared. One of the best methods for inequality proofs is proving that the left-hand side minus the right-hand side in this question, for example, is less than 0. So the left-hand side minus the right-hand side is going to be 2a to the minus a squared minus 2 to the power of minus b squared, which is 1 on 2a squared minus 1 on 2b squared, which, if we made a common denominator, is 2 to the power of b squared minus 2 to the power of a squared on 2 to the power of a squared b squared. Now, since a is greater than b, then this expression is less than 0, since a is greater than b. Because 2 to the power of b squared minus 2 to the power of a squared, well, this number has to be bigger because a is greater than b. So therefore, 2 to the minus a squared is less than 2 to the minus b squared. So again, we've proven that by showing that the left-hand side minus the right-hand side is less than 0. Example 3, we've given that a plus 4b is greater than or equal to the square root of ab, of 4 root ab. For what values will a and b, will the inequality be equal, or will equality occur? So let's assume that 4 plus a plus 4b is equal to 4 root ab. We might square both sides. We're going to get a squared plus 4 times 2 is 8ab, plus 16b squared is equal to 16ab. That would imply that a squared, minusing 16ab, minus 8ab plus 16b squared is equal to 0. And that, of course, is a perfect square. A minus 4b squared is equal to 0. And if we square root both sides, a minus 4b is equal to 0, which means a is equal to 4b. So therefore, equality will occur when a is equal to 4b. Okay, example 4. We've got, if a is greater than b is greater than 0 for real a and b, prove that a plus 1 minus a minus 1 is greater than b plus 1, b minus 1. Again, the best way to prove something like this is to prove that the left-hand side minus the right-hand side is in this case, greater than 0. Now I might just quickly expand that, because these are difference of two squares. So it's going to be a squared minus 1 minus b squared minus 1. Those minus 1s will die, and it's a squared minus b squared. Now that's greater than 0. That's because as a is greater than b. A squared, if a is bigger than b, then a squared minus b squared has to be greater than 0. Now, what I've done here is quite important in terms of how we structure proofs. We don't have to say a squared minus b squared is greater than 0 on another line. If I've stated an equal sign here, I can just say greater than 0 on my next line, and that's telling the person who's reading our proof that means this expression is greater than 0. Right. So therefore, since it's greater than 0, therefore a plus 1, a minus 1 is greater than b plus 1, b minus 1. Okay. Something that I'm pretty sure is not in the syllabus but is quite useful in terms of these types of proofs is the sandwich theorem. So, funny name, but the sandwich theorem basically tells us that if we've got a function that's in between two other functions, then if the functions on either side of the thing in the middle approach some value, then the middle at some point must also approach this value. So we know that sine of x lies between minus 1 and 1, which means that minus 1 on x would lie between sine of x on x, dividing everything by x. However, we're looking at approaching infinity. We know 1 on x and minus 1 on x. As x approaches infinity, they approach 0. Because they're hyperbolas. As any of them approach infinity, they get closer to 0. So therefore, by the sandwich theorem, sine of x on x has to approach 0 as well. So if either of these functions approach the same value, then at some point, this function in the middle must also approach that value. Okay, next one. We might recall the triangle inequality. So the triangle inequality, which we learnt in complex numbers, states that the magnitude of x plus y is less than or equal to the magnitude of x plus the magnitude of y individually. Now we want to prove the converse of that statement, that the magnitude of x plus the magnitude of y is greater than or equal to the magnitude of x plus y. Now I've shown you in complex numbers how to geometrically prove this. In this topic, in our further proof, our nature of proof topic, geometrical proof is not enough. We're going to form an algebraic, a logical mathematical proof that's not just kind of vague and looking at a picture and saying that it looks true. Now we need to look at different cases here. So we're going to look at case 1, because remember the absolute value sends any number positive. It sends any negative number, importantly, to be positive. So we're going to assume first of all that they're both positive, second of all that they're both negative, and then a third/fourth case that one is positive and the other's negative. So let's first of all, we might say case 1, x and y are both greater than or equal to 0. Well, that means the absolute value of x plus the absolute value of y, since they're both positive, is the same as just x plus y. But x plus y is the same as the absolute value of x plus y if they're both positive. So therefore true for case 1. Case 2, let's say x and y are both less than 0. Well, absolute value of x plus the absolute value of y, well, that's the same. If they're both less than 0, it means minus x minus y, which is the same as minus x plus y. But since the absolute value sends any number positive, it's the same as the absolute value of x plus y. The absolute value of minus x plus y in brackets is the same as the absolute value of x plus y without the negative. Case number 3, we might say x is greater than or equal to 0 and y is less than 0. Now often in maths we might say this without loss of generality, or you could say actually write it out, or you could just say without loss of generality. What that means is that this case, it doesn't really matter which one is x and which one is y. It's going to be the same proof whether x is greater than 0 and y is less than 0, or the other way around, because they're not actual specific values, they're just random pronumerals. Right, so we've got the absolute value of x plus the absolute value of y is the same as x minus y as y is less than 0. Now, we could say that this is equal to the absolute value of x minus y. But if y is less than 0, well, we know that this would be x minus y if y is less than 0. And that's actually telling us that this expression here has to be greater than x plus y, which is equal to x plus y, because this expression here would be x plus minus y, or x minus y. So since y being less than 0 makes a double negative, this expression has to be greater than x plus y because of that double negative. Because in this case we've only got a single negative, which means we're going to subtract the y, which makes it has to be less than x plus y. So therefore, since it's true for all three cases, x plus y is greater than x plus y. Okay, we're proving that the absolute value of a squared minus ab plus ab, absolute value of ab minus b squared, is greater than or equal to a plus ba minus b. Right, we might consider the left-hand side here. The absolute value of a squared minus ab plus the absolute value of ab minus b squared. Well, that has to be greater than or equal to all of it in one absolute value. And that's by the triangle inequality. Now, I said this in complex numbers. The triangle inequality is a known quantity. We don't have to state it or prove it every single time. It's a known quantity. If we expanded that, though, this is going to be equal to a squared minus b squared. Notice how I didn't put another inequality sign here, because if I put another inequality sign here, it would be stating that this statement is bigger than this statement here, which it's not. It's equal to this statement, so that's why there's an equal sign there, which is equal to a plus b, a minus b. We're done. So we're proven that this is greater than this, but this is equal to that. Alright, we're proving that the absolute value of a minus b plus c minus b is greater than or equal to a minus c. Well, we know that this expression, a minus b plus c minus b, by the triangle inequality, is greater than or equal to what might we say here? Notice how in this, what we're trying to prove, there's a negative c here. So I'm not going to get it. If I just do what I was about to do, I'm going to get a minus b plus c minus b, and that's not going to get us to here because I've still got a positive c. So since we're taking the absolute value, and if I switch the order of subtraction, it just makes the number negative. But if I take the absolute value, it's just going to be positive, so it ends up being the same thing. So we can say first up that there, and then by the triangle inequality, this is a minus b plus b minus c, which is equal to, the b's will die, I think, b minus a, I think. Again, okay, I made another mistake here. B minus A plus B minus C. Well, doesn't really help us because we've got 2A minus 2B minus A minus C. So let's start again, rub that out. It looks like we don't want to switch the order of this one, A minus B. It still means the same thing. We can switch the order of one and not the other. It still means the same thing because the absolute value, all it does is send any number, negative number, positive. So by the triangle inequality, we can say this is equal to a minus b plus b minus c. And that's equal to a minus c. Now, since the absolute value sends any negative number positive, this has to be positive, which means a minus c has to be greater than 0, which means a has to be greater than c. That's because you cannot take the absolute value and get a negative number. It's impossible. So since a is greater than c, therefore this has to be equal to a minus c, because a minus c, if a is bigger than c, then a minus c has to be a positive number. So therefore, a minus b plus c minus b is greater than or equal to a minus c. Now just back to those two mistakes I made. I didn't make those mistakes on purpose. They were genuine mistakes that I made. But I think it's a good learning curve that you can see that we can manipulate these expressions in many different ways, and we've got to decide which manipulation will work best for the question. So that's important. You're going to make those mistakes, and it's important that you realize what we have to manipulate our question to give our result. Okay, a triangle has sides x, 10 and 12. What are possible values of x? Well, first of all, we know that x, well, it has to be, it could be bigger than 12, it could be the longest side, or it could be the smallest side. So we might say if x is the smallest side, x plus 10, if x is the smallest side, x plus 10 has to be greater than 12, which means x is greater than 2. And if x is the longest side, well, that means 10 plus 12 has to be greater than x, which means x is less than 22. So if x is the longest side, we should know there is a rule in the triangle inequality, so this is by the triangle inequality, that states that the sum of the two smallest sides is greater than the sum of the longest side. So this is by the triangle inequality. You might be thinking, why are there no absolute values? The absolute value is just about taking the magnitude, and we already are given the magnitudes here. And again, the triangle inequality states that the smaller sides have to add to give something bigger than the larger side. So if x is greater than 2 and less than 22, therefore x has to be between 2 and 22. Okay, if a and b and c are greater than 0, prove that this statement is also greater than 0. Okay. We'll look at the left-hand side and we're going to prove that it's greater than 0. So we might have a go at expanding the left-hand side. It's going to be equal to, we expand the left-hand side, it's going to be a squared plus b squared plus c squared minus AB plus BC plus CA, which is equal to, actually that's not true, let's have a go at expanding this properly. So we've got A plus B plus C squared is equal to A plus B plus C times by A plus B plus C, which is A squared plus AB plus AC plus AB plus B squared plus BC plus CA plus CB plus C squared. Now, which is equal to A squared plus B squared plus C squared plus 2 times by all of these things. AB plus BC plus CB. Okay. So we could say that this is equal to A squared plus B squared plus C squared. Now we're minusing, we've got 2 of these and we're minusing 1 of them. So we're going to go plus AB plus BC plus CB. Now we know that A, B and C are greater than 0, so therefore this expression has to be greater than 0. So as A and B and C is greater than 0, then this expression is greater than or equal to 0. Is greater than 0. And we're done. So A squared plus B squared plus C squared is equal to AB plus BC, which is greater than 0, and that's because A, B and C are greater than 0, so there's no minuses there, so we're all good. Okay, next one. Okay, one of the best strategies to prove that A is greater than B is to prove that A minus B is greater than 0. So let's go, okay, x to the power of 4 minus, plus y to the power of 4 minus x cubed y minus xy cubed, and we're going to prove that it's greater than 0. So that's our left-hand side minus our right-hand side is equal to that, which we could say this is x to the power of 4 minus x cubed y plus y to the power of 4 minus xy cubed. We could take out a factor of x cubed here, and so this is x cubed x minus y plus y cubed y minus x. Take out a factor of minus 1 so we can group in pairs. Which is equal to x minus y, x cubed minus y cubed. Now that's a difference of 2 cubes, so we can say this is x minus y times by x minus y x squared plus xy plus y cubed, which is x minus y squared times x squared plus xy plus y cubed. Okay, we're almost there. Now, this is actually greater than or equal to 0, and that's because this has to be greater than 0 because we're squaring a negative number. And since x and y are both greater than 0, this expression has to be greater than 0 because there's no minuses in here. So therefore, x to the power of 4 plus y to the power of 4 is greater than or equal to x cubed y plus xy cubed. Awesome. That's inequalities. Thank you.